Hello, my name is Linus Behling. This is Rack and Return, an equipment checkout system built for CEN5035 with my partner Victor Cabezas. FAU departments all lend equipment, and each tracks it differently. Spreadsheets, notebooks, email, nothing is shared, so nobody can tell where an asset is without asking the department that owns it. Rack and Return replaces that with one web application across both campuses, built from our requirements and design documents. Our requirements specification follows IEEE 830, 31 functional requirements across 7 feature groups: authentication, inventory, checkout, returns, reservations, notifications, and reporting with audit logs. Non-functional requirements cover 8 categories: 3-second search, 500 concurrent users, role-based access control, and single sign-on with no local password storage. 2 requirements shaped everything else: FERPA, since borrower records may be student education records, and 7-year retention. Those are why the audit log is central rather than an afterthought. The design follows IEEE 1016. Rack and Return is genuinely 3-tier. The browser, a PHP 8.4 application on iOS, and SQL Server on a separate virtual machine over TCP/IP. 4 layers with strict downward dependency. Twig templates, controllers, a stateless service layer, and repositories isolating all TSQL behind PDO. That satisfies our modularity requirement. 4 patterns are built: a front controller routing every request through one authorization pipeline, repositories confining SQL, a service layer shared by the web pages and the REST API, and event-driven notifications. 8 entities in third normal form. Status values enforced by database constraints. This traces the checkout use cases, which I am about to demonstrate. Our test document follows IEEE 829 and specifies 36 test cases, 30 functional, 6 non-functional. The criteria are quantitative. Search within 3 seconds against 5,000 records, exactly 1 committed transaction under concurrent checkouts, and unauthorized access denied in every attempt. 2 traceability matrices map every requirement to the cases verifying it. Against the running system, 58 automated checks pass. Let me show you the working system. Authentication goes through single sign-on. To be upfront, this is the development identity provider stub, not FAU's. A student project cannot be provisioned against the university IDP. It reproduces the SAML HTTP post binding with a signed, time-limited assertion, and auth service consumes that assertion without caring who issued it. Swapping in real FAU SSO changes the issuer and nothing else. This is Blake Borrower's dashboard. Look at the navigation. No inventory management, no approval queue, no reports. Those are not hidden by CSS. Every route declares a required permission and the check runs before any business logic executes. The catalog. Each asset carries an asset tag, serial number, category, location, and owning department, and one of 5 statuses: available, checked out, reserved, maintenance, or lost. Filtering runs against indexed columns and returns paginated results targeting the 3-second requirement. I will check out RR0001, the Dell latitude. The transaction is recorded and the status has changed to checked out. Behind that one action, the system verified availability, wrote the transaction, updated the asset, and wrote the audit entry, all inside one serializable database transaction. The confirmation email fires only after that transaction commits, so mail latency can never slow a checkout. Next, we will move over to a staff window. Blake has a pending reservation on the iPad, RR0003. As staff, I open the approval queue, which scoped to my own department, and approve it. The asset is now reserved and Blake is notified. A denial works the same way but leaves the status untouched and carries the staff note back to the borrower. That is FR19 through FR22 and use case 3. Now the part worth watching. 3 assets, 3 states. RR0004 is available and offers a checkout action. RR0001, checked out a moment ago, does not. And RR0003, which I just reserved for Blake, does not either, even though nobody has physically collected it. That last one is the conflict check working. Our checkout logic runs inside a serializable transaction with an update lock on the asset row, and it checks 2 things: whether an active loan overlaps the requested window, and whether an approved reservation does. Most implementations only check the first. This is the second leg. An approver reservation blocks a conflicting checkout even when nothing on loan. That is FR14. And from Blake's own account, the reservation appears under My Reservations with a checkout action because the hold exists specifically for Blake. Collecting it marks the reservation fulfilled inside the same transaction as the checkout. Next, we will go back to the staff window. Now we return, recorded as damaged. The asset lands in maintenance rather than available and is held out of circulation. The exception flow from use case 2. A normal condition sends it straight back to available, and a late return sets and retains the overdue flag. Next, we will log in as a manager. Signing in as a manager. 3 report types: inventory group by status, checkout activity across a date range, and overdue equipment, each exporting to CSV. Notice the navigation again. A manager has no inventory management and no approval queue. Report access only by design. Finally, as an administrator, the audit log. Logins, asset creation, checkouts, returns, and reservation decisions, each with the acting user, the affected entity, a timestamp, and a structured JSON detail field. 2 things make it trustworthy. The application exposes no update or delete path to this table, inserts and selects only, and every entry commits inside the same transaction as the business change it describes, so the log cannot diverge from the system state. And from the staff account, the same URL returns 403. To summarize, all 31 functional requirements are implemented and traceable to a design entity in the SDD, and 58 automated end-to-end checks pass against the running system. 3 limitations worth stating plainly. Single sign-on is simulated by a development stub, since a student project cannot be provisioned against the university identity provider. The development VM runs over HTTP on an isolated private network. TLS terminates at IIS in production, and notification email is captured to a log file rather than relayed through the university gateway. Thank you for watching.